In this lecture, we're going to explore the problem of induction, a famous philosophical problem that goes back to the 17th century. And this will be a two-part lecture. In part one, we'll look at the problem, and then in part two, we'll look at some promising solutions. So let's just get started. One morning, the model Furio woke up. And he drank some coffee, like he always does. Question: why did Furio not worry that drinking coffee would cause hair loss? Maybe it's because every time Furio drank coffee in the past, he did not lose hair. So Furio assumes that drinking coffee today won't cause hair loss, in which case he can do his normal morning hair routine and also keep his modeling career. So in general, Furio assumes that objects behave today as they have behaved in the past. Coffee won't suddenly have new causal powers. In that sense, we are all like Furio. No, not in that sense, Furio. We are all like Furio in that we believe that the past behavior of objects is a reliable guide to their future behavior. All right. So we assume that past experiences are a reliable guide to how objects act in the future. Today's experiences resemble past experiences. This is called inductive reasoning. It's a type of reasoning that explains future experiences on the basis of past experiences. Or perhaps another way of stating it is it explains unobserved phenomena on the basis of observed phenomena. Scientists use this type of reasoning for a lot of their work, this inductive reasoning. So, according, however, to the Enlightenment philosopher David Hume, inductive reasoning is not justified. That is, the type of reasoning that underlies much scientific work is not rationally justified. It's irrational. If Hume is right, that's a devastating blow to the reliability and rationality of the sciences. And it's a cause for concern. So yeah, according to Hume, we have no rational justification for explaining future experiences on the basis of past experiences. So before we look at the problem with induction, we need to do a quick review. So there are two types of arguments: deductive arguments and inductive arguments. Let's take a look at so arguments in general have two components. There's the conclusion, which is supported by reasons, and then there are the premises, which are the reasons that support the conclusion. So in every argument you have what your thesis or your conclusion, and then you have your reasons or your premises for that conclusion, okay? So let's take a look at deductive arguments first. In deductive arguments, when the premises are true, the conclusion is guaranteed to be true. So there are two deductive sins, two ways a deductive argument can go wrong. So when a deductive argument is unsound, at least one of the premises is false. Here's an example. Premise 1, if Davis is a dolphin, then Davis has a blowhole. Premise 2, Davis is a dolphin. Conclusion, so Davis has a blowhole. Obviously, premise 2 is false. I, Davis, am not a dolphin. So, therefore, and I also don't have a blowhole. I am a human. There's a different deductive sin, though. This is a bit trickier for students to spot and understand. It's called invalidity. When a deductive argument is invalid, it is not structured in such a way that the premises guarantee the truth of the conclusion. It's possible for the premises to be true, but the conclusion false, given the way the argument has been structured. So let's take a look at an example of an invalid argument. Premise 1, if Davis is a human, then Davis is an animal. Premise 2, Davis is an animal. Conclusion, so Davis is a human. Now, premise 1 is false. It's true that if I am a human, then I am an animal. Premise 2 is true as well. I am, in fact, an animal. The conclusion is true also. I am also human. So what's wrong with this argument? The problem is that even though premises 1 and 2 are true, the argument is still invalid because it has a structure such that it's possible for premises 1 and 2 to be true, but premise 3 be false. Now again, this has to do with the structure, not the content of the argument. So let's take a look at the structure. Here's the structure. You could replace Davis is a human and with P. So anytime you see the sentence Davis is a human, you could replace that with the variable P, which I've done here. And then you could replace the phrase Davis as an animal with the variable Q, which I've done here. So arguments are kind of like algebra in that you can replace stuff with variables. And we can explore the abstract structure of the argument. So here's the structure. It has this basic form. If P, then Q. Q, so P. Now, if we could construct an argument with this structure, where the premises are true but the conclusion is false, we could somehow replace P and Q with statements such that 1 and 2 turn out true, but the conclusion is false, then we've established that this is an invalid argument because of its structure. So can we do that? Let's take a look. Here's an example. If Davis is a squirrel, then Davis is an animal. Davis is an animal, so Davis is a squirrel. So it has the same structure. If P, then Q, Q, so P. Davis is a squirrel, it's P. Davis is an animal, it's Q. But this argument is no good. Premise 1 is true. It's true that if I were a squirrel, I would be an animal. Premise 2 is true as well. I am an animal. But premise 3 is false. I am not a squirrel. I am a human. So this argument has an invalid form. The form is such that it's possible to have true premises and a false conclusion. Okay, now scientists do use deductive arguments in a lot of their reasoning. But a lot of the reasoning is in inductive arguments, which basically they're not deductive. So in inductive arguments, the premises don't guarantee the truth of the conclusion. Instead, the premises make the conclusion more likely to be true. Okay? So they're not deductive in that sense. They're not, if the premises are true in an inductive argument, it doesn't make it 100% likely that the conclusion is true. And again, a lot of scientific reasoning is inductive. So inductive arguments are what philosophers say is ampliative. The conclusion adds something to the premises. So look at this simple argument. Premise 1, all observed ravens are black. Conclusion, so all ravens are black. So the conclusion contains more information than the premise. The conclusion refers to all ravens. The premise refers only to observed ravens. Okay? So in that sense, the conclusion extends the premises. It adds to it. And there's a lot of scientific arguments that are inductive in this sense. Okay. So inductive arguments then are arguments typically advanced on the basis of past experiences. They use past observations as evidence for conclusions that extend beyond observations that have already been made. We go from the observed to what has not been observed yet. We go from what's been observed in the past and present to what we might observe in the future. So in that sense, we hope that it extends our knowledge. Now, scientific reasoning, again, frequently involves inferring two conclusions that range over events or phenomena that we have not directly observed. So Newton's laws of gravity makes predictions about how planets and other galaxies behave, how their planets and their moons will affect each other's orbits and trajectories. Boyle's gas laws make predictions about how gases will act anywhere in the universe. If you decrease the volume, it increases the pressure, for example, and it increases the temperature. So again, scientific laws describe not just all events that have occurred or that have been observed to occur. Scientific laws also describe events that will occur or could occur. Anytime you decrease the volume of a gas anywhere, the pressure increases. Just like anytime my Uncle Frank feels pressure, he tends to lose it. That was last Thanksgiving. Okay, so it's a good thing that water always freezes. It's a good thing. I'm going to talk a little bit about the notion that, the laws apply everywhere, and not just the things that have happened, but things that will happen. It's a good thing that water always freezes at 32 degrees Fahrenheit and boils at 100 degrees Fahrenheit. Again, I know that at higher elevations, it's different temperatures. But so imagine, though, that if water could suddenly boil at temperatures below 100 degrees Fahrenheit or freeze at temperatures above 32 degrees Fahrenheit. That would suck. Here, you could spontaneously combust and boil alive at room temperature or freeze to death at room temperature. Fortunately, water does not behave that way. At least, so we think. So some inductive reasoning involves inferences from particular observations of the same type to generalizations about that type. For example, all observed chickens reproduce by laying eggs. So we conclude that all chickens reproduce by laying eggs. On the other hand, all observed individual dogs do not reproduce by laying eggs. So we conclude that all dogs do not reproduce by laying eggs. In fact, other scientific arguments pull from multiple types of evidence. So evolutionary biology, for example, draws from the fossil record, from DNA analysis, comparative DNA and genomic analysis, and from comparative anatomy. However, both kinds of inductive arguments rely on the assumption that the instances we have direct experience of are reliable guides to instances that we have not experienced directly. However, according to the philosopher David Hume, in fact, there is nothing logically inconsistent with the future being radically unlike the past. It's possible that the sun won't rise tomorrow. It's possible that a dog will lay some eggs. So here's a little thought experiment. It's the what world are you in thought experiment. Take two different worlds, alpha and beta. In the alpha world, nature is uniform. Okay. For example, sunlight causes plants to grow. Sunlight does not cause human hair to grow. Sounds like our world. Take world beta. In world beta, nature is not uniform. In world beta, sunlight causes plants to grow, but not human hair, up until the present moment. So up until the present moment, right now, sunlight causes plants to grow, but it does not cause human hair to grow. So up until the present moment, world beta is like world alpha. It's a lot like the world we're in right now. But up until the present moment, that is. Then at the present moment, guess what happens? After the present moment, sunlight causes human hair, not plants, to grow. So, it's one more reason to rethink sunbathing. So here's a question for you. Which world are you in? Are you the world where nature is uniform? Or are you in the world where nature is uniform up until the present moment, in which case the laws will radically change? Or maybe they'll change tomorrow. This is a skeptical dilemma. The fact is, you probably don't know which world you're in, and it's probably not possible for you to know which world you're in. So according to David Hume, then, we can't suppose that the future will resemble the past without begging the question. You've heard this phrase probably before. Let's explore what it means. So you beg the question when you assume what you should prove. So you assume the very thing you should prove. Instead of proving something, you just basically state over and over again what you're trying to prove, as if that's evidence for what you're trying to prove. Here's an example. Saying that you're the best katana swordsman because you're the greatest katana swordsman. Best and greatest are synonyms. They mean the exact same thing. So this fellow has not proven that he is the best or greatest katana swordsman. He's just stating the conclusion over and over again. Is that a picture of me when I was 14? I guess you'll never know. So according to David Hume, the reasons we believe that the future will resemble the past are merely that we assume that the future resembles the past. But, according to David Hume, it is actually false that the future must resemble the past. That the future should be like the past. That objects will behave in the future the way they've behaved in the past. So Hume includes cases that we believe we have powerful evidence for. Like, we think rocks must always fall. Hot pans must always burn. Sticking metal in live sockets must electrocute you. We think these are allegedly reliable beliefs about objects. So we assume these beliefs are reliable. Hume challenges this, though. According to Hume, it's not the case that rocks must fall. It's not the case that hot pans must burn. It's not the case that sticking metal in live sockets must electrocute you. Again, it's a logical issue. It's logically consistent to say that in the future things will not behave as they did in the past. So philosophers have worried long about Hume's problem, and they've offered several kind of responses in the past that we'll explore. The first response comes from causal reasoning about causes and effects. So perhaps our grasp of causal relations explain and justify our confidence that the future will resemble the past. Okay, our beliefs that objects cause certain effects to happen. They have certain causal powers. For example, hot potatoes burn my hands because they are hot, and heat causes the skin to be damaged. Okay, so our belief that hot potatoes burn is because hot potatoes are hot, and heat is a power to cause burning, basically. Bill got sick from eating raw steak because raw steak causes food poisoning. Okay, which is why you should cook things properly. Hume challenges this, though. Hume says causal reasoning will not save you. The problem of induction is still there. According to Hume, the mere inspection of objects, no matter how careful, does not reveal conclusions about their causes or effects. So, take an example. Take a piece of wood and inspect it with the 5 senses, all right? Seriously, look at the wood. Touch the wood. Smell the wood. Listen to the wood. Taste the wood. Looking at, smelling, touching, tasting, or hearing wood does not tell you that fire burns wood. It also does not tell you that wood floats. How do you find out that fire burns wood or that wood floats? You learn that wood burns by burning wood. You learn that wood floats by observing wood floating in water, okay? So we gain causal knowledge through experience. When one type of event regularly occurs after another, and the two events are spatiotemporally contiguous, it just means that they're near to each other in space and time, they touch each other, then we believe that the first event must cause the second event. So when one type of event regularly occurs after another type of event, and the two events are close to each other in space and time, we believe that the first event must cause the second event. For example, you strike a match, the match burns. So you'll believe that striking a match causes a match to burn. Event 1 causes event 2. You regularly observe it, and you conclude it. You flip the light switch, the light goes on. Over and over again, you assume that the one causes the other. But here's the deal. According to Hume, our causal knowledge is dependent on past experiences. So Hume argues that our causal knowledge cannot justify our belief that the future will resemble the past. Sorry. We cannot use our causal knowledge to justify induction because we use induction to justify causal knowledge. Again, you can't use one to justify the other because you use the other to justify the one. This is that same thing we just saw a few slides ago. It's begging the question. Or another term for it is circular reasoning. Circular reasoning is basically a synonym for begging the question. It's assuming, again, what you need to prove in an attempt to prove what you assume. Like these two skydivers who are both going to die if they don't deploy their parachute. Doesn't matter if they're holding each other up, they're both going to fall. So our belief that fire burns wood in the future is based on the belief that the future resembles the past. We've seen fire burn wood in the past, so we assume that fire will burn wood in the future because we believe that the future resembles the past. But again, Hume says, what is the basis for that belief? And again, according to Hume, there is no rational reason to hold that the fire must burn wood in the future. You just beg the question, or you give circular reasoning. It's a mere psychological projection instead. So let's look at some responses to Hume, some additional responses to Hume. Here's a response. Our inductive reasoning worked in the past, so it will work in the future. Is this a good response? Well, here's the deal. This begs the question, again, it's another case of circular reasoning. Hey, it worked in the past, so it'll work in the future. We're trying to justify the very belief that we can assume that the future will resemble the past. And you can't say the future will resemble the past because in the past the future resembled the past. You can't say that inductive reasoning will work in the future because inductive reasoning worked in the past. Again, this is circular reasoning. Here's a better, perhaps more promising response to Hume. Let's just downplay the significance of the problem. Of course, past experiences don't guarantee that the future will resemble the past. But, however, the absence of certainty is not a problem. Science is fallible, it's changing. So we'll just settle for reasonable doubt over certainty. Okay, it's good enough. So this seems more promising. After all, inductive arguments aren't deductive arguments. No one ever said that inductive arguments guarantee that the conclusion is 100% likely to be true. Only that it raises the likelihood of the conclusion. Some problems with this though. The target of Hume's challenge isn't not mere certainty. Instead, the target of Hume's challenge is any reason to suppose that the future resembles the past. Take simple induction. Swan 1 is white. Swan 2 is white. Swan 3 is white, etc. So probably the next swan I observe will be white. Here's the problem though. You can't even justify that the next swan will probably be white, according to Hume. You need knowledge of objective facts about the probability of particular statements about swans that is not based on the observed frequencies of swans. But on the other hand, if your belief is based on observed frequencies, again, you beg the question and assume the future will resemble the past. Here's a caveat though. Of course, scientists rarely claim certainties. Even though scientists sometimes claim they have proven a claim, what they really mean is that there is a preponderance of evidence. Preponderance is a technical term that means buttload. So here's an example. Scientific conclusions can be trusted in. So here's maybe as long as they've passed a battery of tests, then, we can trust them, we can rely on them. So for example, the claim that heat evaporates water perhaps it's passed a battery of tests. So we can put our confidence in the claim that heat evaporates water. Because every time water is heated, the water evaporates. Okay, seems pretty reliable. But there's an objection to that. There's nearly always an alternative hypothesis that is consistent with the results of the same tests. So just mere consistency is not enough. What do I mean by that? Well, scientists look for more than mere consistency though with data when they assess hypotheses. So anytime scientist heats water, the hypothesis and water evaporates. So here's the hypothesis. Heat energy breaks the hydrogen bonds between water molecules. Okay, seems plausible. Hypothesis 2. Heat energy breaks the hydrogen bonds between water molecules, and at the same time, invisible angels jiggle the water molecules free. While both of these hypotheses are consistent with the observational data, it's possible that heat energy is breaking hydrogen bonds and angels are jiggling the water molecules free at the same time. But hypothesis 1 is simpler. So isn't that better? Many scientists, again, suggest that simplicity plays a role in scientific reasoning. But simplicity is hard to pin down. Does it mean less entities? Like we just posit less types of things that exist? So like one says there's just molecules and the other says there's molecules and angels? Or is it less laws? Sometimes a simpler hypothesis with less entities will have more laws. Or perhaps it just means less sentences in a theory. So you'll have a few laws and a few entities, but then a ridiculous amount of sentences. Like, what should we value more? It's not always obvious. Again, why should we prefer simpler to more complex theories? Why should the world be simple? Enlightenment scientists appeal to God, saying that God would use the most efficient means, but I don't think many scientists today would appeal to that in their explanations. In fact, in a lot of contexts, its complexity is the king, like ecology, for example. Well, there's other theoretical virtues besides simplicity, okay? And I'll go through these quickly because I think I have a whole other lesson on this stuff. But like, we also like theories that explain more, all right? So they're broader in explanatory scope. For example, Einstein's theory of relativity was able to explain everything that Newton's theory could explain, plus there was phenomena that relativity explained that Newton's theory did not explain, like very fast moving objects, things at near light speed, and very, very massive objects, for example. We also like theories that are more precise. Again, Einstein's theory was more precise than Newton's with respect to predicting certain motions. Which is why today GPS satellites use Einstein's equations instead of Newton's. Otherwise, they would be off by several hundred meters. So Einstein's theory is more precise than Newton's. We also like theories that are consistent with other well-confirmed scientific theories. And again, Einstein's theories are consistent with various electromagnetic phenomena, sunlight deflection, etc. Okay? So again, theories that are more broad, more precise, and then consistent are better than theories that are less broad, less precise, less consistent. So that seems like a promising way, right? Not always. Appealing to these theoretical virtues is not always decisive. Take two theories, theory 1 and theory 2. Both are simple. Both are precise. One is narrow, but consistent with a well-confirmed scientific idea. The other is more broad, but inconsistent with a well-confirmed scientific idea. So should we prefer theory 1 or 2? Both have 3 virtues and 1 sin, you could say. But they're different sins and different virtues. Should we value broadness more or consistency more? It's not always obvious. Another thing is, we should talk a little bit more about explanation. So many scientific pursuits don't just want to merely describe what's going on, but they want to explain what's going on. Why is the ocean salty? Why do lions have manes, but not cows? Straightforward inductions don't really explain very well. Inferring that all ravens are black from a sample of black ravens does not explain why ravens are black. We want to know why something has a particular feature or property, like reproductive success. So theories that explain, they're better than theories that merely describe. But, again, the criteria for a good explanation is not obvious. Is it explanation by mechanisms, by laws, by predictive power? Also, is a good explanation one that's simpler, narrow, precise, broad, consistent? What happens when 2 explanations tie? Okay. So it seems like we lack a convincing general defense that hypotheses that are simpler, more explanatory, broader are always preferable. So again, we lack a response to the problem of induction. We lack a helpful response to what justifies inductive inferences. And this is a problem because ordinary humans and scientists both rely on induction for important decisions. So this is the end of part 1. In part 2, we'll look at some more promising solutions to the problem of induction.